At your company, someone before you took a big block of addresses and subnetted it into smaller pieces, determining a number of subnets and a size of each subnet. In this video, we'll talk about that whole process and how you can predict how many subnets exist and how big they are. Content-wise, we're in the middle of a chapter that I call Perspectives on IP version 4 Subnetting. In the books, it's in volume 1, and the part about IP subnetting, it's currently in chapter 11 in the current edition. So what's that mean, perspectives? Well, it's not about every last little detail. It doesn't take you through every topic and all the minutiae you'll need to know. But here's what it does. It begins by talking about, hey, look at a network diagram and visualize, learn how to visualize where subnets exist. Then inside one subnet, visualize where we'll use individual IP addresses. The previous video then looked at what big address block can you possibly use to allocate for your company. And then in this video, we'll talk about taking that address block and choosing some big ideas about how to subdivide one block into a bunch of smaller ones called subnets. And in particular, in this video, we'll talk about making one choice of a subnet mask that subdivides the network, and that sets the size of the subnets in the network, and how to interpret those choices of masks. I'll show you lots of examples. And then when you make a choice of one mask to use for all subnets, which will be the assumption we make here, you can predict all the subnet IDs, and we'll talk about listing all those subnets at the end of the video. All right, as always, stick around to the end. It's like you're in my CCNA study group. I'll give you advice. We'll have a review exercise here at the Network Upskill channel, and additionally some quick advice about how to best use the books to stay on top of this video's content. We're going to talk about choosing one mask to use to subnet an entire network. So to do that, let's talk about a network. Let's talk about a Class A network. So the concept with a Class A network is that all addresses in that network have the same value in the first single octet, and then different values in any of these last three. And because those last three octets combined contain 24 bits, there are 2 to the 24 combinations of values out here. All right, 0 through 255 there and there and there. That's a lot of combinations. That's over 16 million possible numbers in a Class A network. So if we take private Class A network 10, for instance, and we describe it, that means all addresses that begin with 10 and anything within these ranges in those last 3 octets. Now, numerically, we describe that as network 10 with its default mask, and its default mask is /8. What does that mean? It means the idea of all that begin with 10, that is the first octet of 10, well, one octet is 8 bits long, so the part that's the same, the prefix, if you will, the part that's the same in every address is 8 bits long. And that's the meaning of this /8 in the subnet mask, the part that's the same amongst all addresses in the group. So when we go to subnet, we'll choose a different mask that has more ones in it, a bigger number, a longer prefix. For instance, maybe we take that network 10, which is over 16 million addresses, and we say we're gonna make a subnet that's smaller, and it's gonna be smaller because, hey, one subnet's gonna be all addresses that begin 1011, that one. Now, 1011, that part takes up 3 whole octets. Each is 8 bits wide. That's 24 bits long. So our mask is /24 in that case. It's everything in the entirety of those first 3 octets. And if we use that same mask for other subnets, we might have a subnet then of all addresses that begin with 1012 and another of all addresses that begin 1013 and so on. And those would be some subnets we could use. And the idea hopefully is intuitive at this point, even if you couldn't go out and do the math in every instance, all right? Where you could say, all right, I kind of get the idea of we're breaking this network down into smaller pieces, and I accept, Wendell, that we're doing that with this idea of a /24 mask. Now, the values for each of the Each of these subnets, the way I've set it up, first 3 octets must be the same now. First 3 octets, 3 times 8 is 24. We're using that mask. And the values will range between 0 and 255 in that last octet in each case. So in terms of breaking up our Class A network 10 into subsets called subnets, here are the identifiers, the subnet IDs for those subnets. Here's a representation of the first 256 subnets. 10.0.0.0, 10.0.1.0, 0.20, and so on. Like 10.0.3.0 means all that begins with 10.0.3, all that begin with 10.0.4, and so on. When using this mask, the mask meaning all whose first 24 bits match this number. And then there's a bunch more that start with 10.1, 10.1.1, 10.1.2, 10.1.3, and more. And there's a bunch of them with this design, all right? So you could write down what all those are or put them in a spreadsheet for tracking. But the person who made this up, they thought like this. They said, I'm starting with a Class A network. Class A networks always have 1 octet that's the same before I subdivide it. Let me say that again. Class A networks always have 1 octet that's the same before it's subdivided. And so we think of that first octet or first 8 bits as network bits. And then the designer says, I need to create some subnet bits to identify and number subnets with. So they take that original dividing line that was at the 8-bit mark and they move it out to the right. And that's what this open lock is meant to represent. It's unlocked and we can move the dividing line to somewhere out in here. And we moved it, in this case, to the 24-bit mark. So the dividing line was at the 8-bit mark, and we moved it out to the 24-bit mark. So we actually added 16 or created 16 subnet bits in here. So we were at 8, now we're at 24. So that's 16 subnet bits. And it turns out with this plan, we created 2 to the 16th subnets. Interesting, huh? Remember that previous page with that long list of what the subnet IDs were? Yeah, there were 2 to the 16th, or over 65,000 subnets created. Then with this 24-bit dividing line, since IP version 4 addresses are 32 bits long, that left 8 bits over at the end of the structure of these addresses. We would consider the host bit field to be 8 bits long. Inside each individual subnet, the number of numbers in the subnet is 2 to the number of host bits, 2 to the 8th in this case, but 2 of those values are reserved and can't be used by a host, can't be used as an IP address. So the calculation of the number of usable addresses in a subnet is 2 to the h minus 2 for the 2 reserved addresses. So in this case, 8 host bits, 2 to the 8th minus 2 is 254. So on this page, I can take you through the details a little more formally. So if your starting point is a classful network, you figure out the class A, B, or C, and that determines whether the network part is 8, 16, or 24 bits based on 1, 2, or 3 octets of the network part. Then you're given the mask that the designer made up, like /24 in the examples so far in this video. And that sits out here. We'll just show it as /P, P for prefix bits. And then it's just a math problem. Network plus subnet plus host equals 32. And you figure out the size of the subnet and host fields. All right? So that's the idea. Now, if you're not subnetting a class A, B, or C network, you can't make that assumption about 8, 16, or 24 bits up here. But if you're using a CIDR block instead of a class A, B, or C network, the block size that you're assigned by a regional registry or an ISP, they tell you how wide this block size is. All right, so you know how big that is, and then whatever mask you choose to use, it's a simple math problem of saying the block size width plus the subnet field plus the host field needs to add up to 32. You'll know how big the subnet field is, how big the host field is, and you can do that bit of math to figure out how many subnets did the designer create and how many hosts are there in each subnet. Today's video is sponsored by me, yes. And if you'd like to support the channel, there's something you can do to help. If you start out in my link tree, just go to that link and click products. There's a way to get to Amazon and to Cisco Press. Go to Cisco Press to buy books, go to Amazon to buy literally anything. And if you do, it doesn't change the price, but those companies will give me a few dollars back from the sale. It's a way to help support the channel and a way to say thanks, and I'd very much appreciate it. All right, back to the content. So let's talk some more about some big ideas and some related math. You're starting with a class A, B, or C network right now, okay? So you can think of that as a 3-part address structure or a 2-part, and it's useful to think both ways. And we just talked about it, but let's talk about it some more now. There's a network part based on the class, 8, 16, or 24 bits long, and then you'll have a mask. And if you think about the mask as a slash and a number, that's prefix notation, it basically tells you this dividing line between the subnet and host part. It also tells you this dividing line between the prefix and host part. In fact, in that earlier example, slash 24 right here in that example basically says the prefix part is 24 bits long and everything else to fill up the 32-bit structure is the host part because the width of the whole thing is 32 bits. Now, the designer makes a design choice about a big concept of saying, do I want to use one mask and one mask alone for all subnets, or do I want to change and use different masks for different subnets? Both are valid choices. If you use different masks, you can make large subnets, medium-sized, small subnets. You're not as wasteful of addresses, but it means the people using the network have to be better at subnetting math on a day-to-day basis. It's more complex. So sometimes people do like I showed in that previous example where it's only mask slash 24 in all subnets and it's just easier to operate. All right. So in the rest of this video, I'm going to assume one mask for all subnets just so we can talk about that angle on things. All right. So if using one mask only for all subnets, the number of subnets created in a network can be identified, the sum total of them, as 2 to the number of subnet bits. And then the number of hosts in each and every subnet is that 2 to the h minus 2 calculation we talked about just a moment ago. Let's spend just a moment on the calculations. The math is, 4th grade math, but it's just remembering the context, all right? So here's the deal. If you're starting with a class A, B, or C network and subnetting it, the network part, the width of the network part, is determined by class A, B, and C rules. It's 8, 16, or 24 bits wide, depending on the class being A, B, or C. So that's the first thing to start with. And then you look at the choice of what one mask did the designer choose. That would be this dividing line out here. So it turns out the network and subnet part combined equals the prefix length in the mask slash whatever in the mask. So let's say it was 24. Well, we know network plus subnet equals 24. If the mask was slash 20, network plus subnet bits equals 20. If it's 28, they add up to 28. So with this little equation, you can calculate the number of subnet bits. And again, if you've got the mask and prefix notation, whatever the number is for the mask, the prefix and host part, they add up to 32. Pretty simple math to figure out how wide is the host part. Then you can calculate the number of subnets and the number of hosts per subnet. Last angle on the process, what if you're not subnetting a class A, B, or C network? You're subnetting a CIDR block. Well, if you're not starting with a network, you can't start with class A, B, and C rules. But the CIDR block you're assigned also the number that is the width or the number of bits defining the CIDR block. It could be slash 14, it could be slash 17, whatever. So that would be this dividing line. But the block size's width plus the subnet would be the same as your site's chosen mask. So now it's the prefix of your mask is the block size plus the number of subnet bits. And then you can pick up that bit of math. All right, so now let's take a look at some examples. Examples really do help. So I'm going to show you 5 examples that begin with a class A network, but with different masks, in this case, slash 18. So again, the context is Subnetting a Class A network, the designer's choosing to use one mask and one mask only for all subnets, and that mask is /18, meaning in each subnet it's the first 18 bits that are the same in every address. So the questions I'd want you to answer are, how many network bits are there? How many subnet bits? How many host bits? In other words, what's this structure? And from there, you can calculate the number of subnets created and the number of hosts per subnet. So rather than just write numbers in this table, I'm going to re-show the structure, but now with 8, 10, and 14 bits in those fields. Why 8? Class A, from memory, we know Class A networks have 1 octet or 8 network bits. With the mask we're using, /18, you remember that the network plus subnet bits should add up to the prefix length of 18, so 8 plus 10 gives us 18. And then all three fields should add up to 32, so 8 plus 10 gives us 18. We need 14 more to make 32, so we've got 14 host bits. So then if, say, an exam were to ask you, well, how many subnets would be created by this particular structure, or this particular design choice, 2 to the 10th subnets with 2 to the 14th minus 2 usable addresses in each subnet. So there's one example. Let's do another. Example 2, we're still subnetting a Class A network, but the design choice in this case was to use a /20 mask. So the logic again is the same. We start with 8 network bits for the same reason of having a Class A network, but these first two fields, the network and subnet part, need to add up to 20 in this case. So we've got 12 subnet bits. Then all three together need to add up to 32, so 8 plus 12 is 20, so we need 12 more bits to make up the 32 bits. Then these calculations give us the number of subnets created and the number of hosts per subnet. How about another one? Still subnetting some Class A network, but in this design they chose a /22 mask for all subnets. So what's our structure look like? Well, it's Class A, so we've still got 8 network bits, but network plus host bits have to add up to 22 in this case. That means 14 subnet bits, leaving 10 host bits, which would have given us 2 to the 14th subnets with 2 to the 10th minus 2, or just over 1,000 addresses that are usable per subnet. So hopefully it's starting to make a little more sense now with all these examples, but let's do example 4, still subnetting some Class A network, now with the /24 mask. This matches that first example that we saw with network 10. So with a Class A network, there are 8 network bits, that first octet. But with a /24 mask, the subnet field is 16 bits long. 8 plus 16 equaling 24. The three fields together need to add up to 32. That leaves us with 8 host bits. So we end up with 2 to the 8th minus 2, or 254 addresses per subnet, with over 65,000 subnets created with this design. This is a very popular choice to use private Class A network 10 with this mask. It's a very simple mask to use as well. In the last Class A example, this time we've got a /26 mask. So the same logic, just different numbers. 8 network bits because it's Class A. 8 plus 18 sum up to the mask's length of /26. And that leaves 6 host bits because the three fields add up to 32, giving us 2 to the 18th subnets in this design with 2 to the 6 minus 2, or 62 usable addresses per subnet. Well, if you found those useful, let's do 5 more. We'll do a couple on Class B and a couple on Class C. In this case, we're going to subnet some Class B network, and the single mask chosen by the designer is a /22. So the first change here is to build this structure down at the bottom. It's a Class B network, so we've got 16 network bits. I've even shown that a little bit wider down here at the bottom. And we know that our chosen mask, /22, the network plus subnet bits need to add up to 22, so that leaves us 6 subnet bits. 16 plus 6 is 22, leaving us 10 host bits. So with this design, we get 2 to the 6th subnets and 2 to the 10th minus 2 addresses per subnet. So another Class B example now with a different mask, /24. So similar logic, we ended up with 16 network bits. 16 plus 8 gives us 24, so we've got 8 subnet bits. That leaves 8 host bits for 2 to the 8th subnets and 2 to the 8th minus 2 addresses or hosts per subnet. Now, that one might be a popular choice too, just because the mask gives us 24 prefix bits, which is on the boundary between the 3rd and 4th octets. It makes it easier to work with mathematically. If we were to use that mask, we would end up with numbers like these: 172.16.00, 102.030, all the way up through 172.16.255.0. That's the pattern of the 256 available subnet IDs that you would use. Turns out the number that ends in 0 is reserved in each subnet, and the number that would end in 255 in this case would be reserved in each subnet, leaving 254 addresses per subnet. All right, back to more examples. We're back to a Class B network now with a /26 mask. So because it's Class B, we have 16 network bits. We've got 10 subnet bits because 16 plus 10 adds up to 26. 16 and 10 is 26. That means we need 6 more bits in the host field, so they all total up to 32, giving us 2 to the 6th minus 2 hosts per subnet and 2 to the 10th subnets. For this first Class C example, we've got the Class C network, and the one and only one mask used when subnetting this network is /27. So they're so small, these Class C networks. Would you bother? Well, yes, you might, and you might use a mask like this. So what do we get when we use that mask? Well, because it's Class C, you have 24 network bits. Because the network and subnet part should add up to 27, you get only 3 subnet bits. Because all 3 fields add up to 32, you get 5 host bits. So you don't get a lot because you didn't start with a lot of addresses, but you get 2 to the 3rd subnets, or 8 subnets, and 2 to the 5th minus 2, or 30 addresses per subnet. Then one more example with Class C. Say we chose a /29 mask to use with all subnets. Because it's Class C, you've got 24 network bits. The network and subnet bits need to add up to 29, so you'd have 5 subnet bits. So we'll have a few more subnets in this case compared to the previous example. But since they all add up to 32, only 3 host bits, so not as many hosts per subnet. So in this case, we've got 2 to the 5th subnets with 6 addresses per subnet in that case. There is one more step I want you to think about in a practical case of how you would use this information. So backing up, in the previous video, we talked about how you need to pick the large address block that you're going to use. It might be a public IP network, a public CIDR block, or a private network. And the rules for which one you might use have changed over the decades, and that's probably already happened at your network, all right? You just need to figure out what did happen so you know what you're working with. And then someone has chosen already, probably. Are you using one mask for all subnets, or are you using many? If it's one mask, what is that mask? And they'd choose that one mask, by the way, to make sure it accommodated the largest subnet that you'd need, the largest number of addresses in a subnet. If you're using many masks, it might be that they make a choice to say, we don't want to support every mask known to man. They might say, hey, we want one mask for extra large networks, one for large networks, one for medium-sized networks, and one for small networks, maybe 3 or 4 sizes, and get used to those, all right? But you make your mask choices. But if you chose to use one mask for all subnets, it's easy to pre-list what all your subnets are, so then you can keep track of which ones you've used and which ones you haven't. But if there are many masks, it's honestly impossible to pre-list them. You just have to say, when I choose to use some new subnets, I pick them, and then I have to update my list of what's used based on what I did choose to use, all right? So if we assume there's one mask in use, I say pre-write your list. So here's the idea. If all subnets of Class A Network 10 were to use a /24 mask, here's the pattern of what those look like. And you could put these into a spreadsheet and track them. Now, that'd be a lot of subnets to put in a spreadsheet. There are actually software tools built to do this for you. They're called IP address management tools. And you could tell it what your network is, what your mask is. It could go out there and scan the network and see what exists and see that, certain ones are in use and that kind of thing. But if you're just making a list in lab to keep track of things, you could say, hey, here's the first subnet, and here's the second one, here's the third, and so on. And by the way, the first two are in use, and here's where they're used. And that's very practical information to keep. Also, in every subnet, the subnet ID and the subnet broadcast address. Subnet ID is the numerically lowest number. Subnet broadcast address, the numerically highest number in the subnet. They're reserved and can't be used as addresses, but everything in between, those are the usable addresses. You may understand that by the time you study through for CCNA, but others may not. So you could add that kind of information into your tracking table as well. So make your list of subnet IDs and other useful information to track. Now, if you happen to subnet that same network with a different single mask, your list of subnets will be different. Here's the pattern if you were to use a /20 instead of a /24 mask, as it turns out. And then you might have a beginning of a table like this with those subnet IDs and those subnet broadcast address. But the concept is the same. I'm just saying somewhere, either with specialized software or a spreadsheet, you're going to want to keep track of what subnets exist on paper and which ones you've actually used. So just one more example of that. If it's a Class B network like this one and with the /24 mask, here's that pattern of subnet IDs that I mentioned earlier, and you'd keep those in a table, these different subnets of network 172.16, and keep track of where they're used as well. Hey, welcome to the end of the video. Thanks for hanging with it. All the videos related to this chapter are about perspectives, big picture ideas. There are some details, but the idea is I really want you to get the big picture ideas. So if you get those, great. You're going to see the details again. For instance, all those details about 2 to the number of subnet bits and 2 to the number of host bits minus 2 and so on. We're going to revisit those in the third chapter on subnetting. That's currently chapter 13 in the now current version of the books. So don't worry about it if you didn't catch every little detail, all right? But there is practice. So here at the channel, the next video in sequence is a review video. It's an exercise where you get to practice interpreting that mask choice by calculating how many subnets in the design and how many hosts per subnet, very much like those 10 examples that we just walked through. So look for that. Then also, you should read the book chapter with these perspectives, but don't do it yet. I want you to watch all the videos related to this same chapter, get those in video form, then maybe give it a day or two, and then just skim through the perspective chapter in the book, get those big picture ideas flowing. We want it to be natural to think about, well, what does the world work like with IP version 4? So it's just normal for you. Thanks for hanging to the very end. If you're ready for more instructional videos on this topic, there's one more related to this perspectives chapter. Click on the left to reach that. It's about implementing the design that you just understood. If you want that review video we just talked about, click on the right and go practice that calculation of 2 to the S and 2 to the H minus 2. All right, thanks for hanging out. I'll talk to you soon.